Right, this lesson, the final bit of chapter 7.4, we're going to look into the final scenario 3, a drawbridge, which is not very common, but when it comes up, students do always get confused what to do. So before I go through the example, I'm going to help you visualize and actually feel it physically, literally, the forces inside the drawbridge. So what I want you to do is, if the environment is safe for you to do, and if you're in a room where you've got sofa or bed, that would be perfect. So what I want you to do is on a sofa, on the sofa or bed, whatever, where you can lay down. So I want you to lay down. That's you laying down, and then I want you. So that's your feet. So that's your leg. I don't know why they come up. And then, so what I want you to do is I want you to lift up your leg. Straight. So the straight, lift up your leg in an angle like this. So lift up and lift down. So up and down. So I would like you to fill in, feel how your hip feel when you lift up your leg, because that's exactly what the drawbridge actually is happening inside the hinge. So that's the hip is actually essentially is a pivot. So when you lift up and down, how do you feel the muscle inside the hip working? Now, so sorry, there was a bit of disruption. Carry on. Next, I'm going to show you a video. I want to have a look at the drawbridge. So it works. Now, think about all the forces on this side of the pivot. What forces are put on in there? Think about the direction of the forces being put on there. So the forces, that will be put on the drawbridge is, now imagine, if you don't know what the forces, the direction of forces, think about if it breaks, if it breaks, that hinge breaks. In what direction would it break? So first of all, we know, as you lift up, think of it, this is your leg, think about this, your leg. As you lift up your leg, that's your hip, that's your toes. As you lift up your leg, you feel actually, the reason I'm asking you to do on a sofa is because you can feel the weight or your hip is actually will be pushing down. That's because, well, that's normal because there's a force going down. As you lift up your leg, there's a force actually going down. All right. And what else? You will actually feel the muscle pulling into your body like this way as well. So, in other words, when you lift up the bridge, these are the forces that the bridge is exerting onto the hinge. Now, going back, therefore going back to reverse, because we're looking at from the hinge perspective. So from the pivot, therefore the support that has been given to the hinge, to the drawbridge is going up, counter that one, so reaction 1, and then also countering the inside force by pushing outwards R2. So these two are the forces that are on the drawbridge, on the hinge, specifically on the drawbridge. So let's go back to this question here. Let's have a look. So a uniform rod of mass AB is smoothly hinged at A. So this kind of question is a drawbridge question. So first of all, I know there will be a R1 and there will be a R2. All right, so these two forces are the same as the one that I show you in here. It doesn't matter which one is R1 and which one is R2, but essentially from the hinge, there's a support going up and the support pushing out. So going up and pushing out, going up, pushing out, that's R1 and R2. So that's a reaction, that's a support given by the hinge on the wall. So that too is a special one, specifically for the drawbridge. What else? A light inextensible string. So when there's a string, we know there's tension. The tension is always pointing towards the point where the string was attached to. So the string was attached from the point D, therefore tension will be pointing upwards. Vertically above A. So if the string keeps the rod equilibrium position and angle between the string is 40 degrees. So what we're told is this is 40 degrees. So I've given that. What else? Calculate a strain, the tension and strain, the magnitude and direction of the rod exerted on the rod by the wall. So we'll talk about that later. Let's have a look. The mass of 6 kilogram uniform rod. So 6 kilogram right in the middle. 6. Oh, actually, let me use blue for forces. You know, I've been using blue color for all the forces. We've got 6G shooting downwards. Length 4 meters. That will be 2 meters. And this will be 2 meters. Are we told about AC? Yes, AC is 3 meters, so therefore will be 1 meter. Right. So remember the steps. First step, like the previous one. First step on the here, upward force equals downward force, left equals right. So step 1, up equals down, left equals right. So these two are the equations we have set up 2 equations. But T is diagonal, so we have to resolve T first. So I'm going to put in here again. T is diagonal. So we need to resolve T first. To resolve T, we can actually use this triangle in here already. So if you want to, you can use this triangle. Sorry, what is not working? So you can use this triangle in here, essentially. I'm going to just draw out. So to resolve T, that's my T. X is going to your left, Y is going upwards. So that's 40 degrees. So X equal T cos 40 and Y equal T sine 40. Now with these two forces, then we can set up equals down, left equals right. Okay, so upward forces. Upward force is, so force pointing up is R1, so up equals down. Upward is R1. What else? The Y component of T, which is T cos 40 plus T cos 40. So what's pointing down? 6G, so 6 times G. 6G, put in a calculator, 6 times 9.8. I believe it's 58.8 or something, 6 times 9.8. Oh, yep, 58.8. If you do mechanics more, you will actually know the 9.8 times table as you do more. Now, cos 40 is not a nice number, so I'm going to leave it as it is, 58.8. I'm going to leave it like this because there's nothing else I could do. Right, or maybe I could make R1 a subject because I know down the line that we'll see with his equation. How do you know? Well, there are 2 variables in it. So, yeah, so R1 equals 58.8 minus T cos 40. So next, left equals right. So forces pointing left is the X version, the X component of T cos 40. Oh, actually, it was meant to be T sine 40. I don't know if you picked up my mistake, actually. From the first equation, I made a mistake in here. It should be a T sine 40 because that's the Y version. That's the Y component, T sine 40, my bad. So for the X, that will be T cos 40 to the left and to the right with R2. So T cos 40 equals R2. Right, so we've got 2 equations in here. I'm going to label them equation 1 and equation 2 because I'm going to use it later. Next step, do you remember what's the next step? Take moments at the point. So step 2, take moments at the point. So we're going to take moments at, now, I'm going to take moments at A. Okay, going to take moments at A because R1, R2 on it, so you can ignore calculating moments for 2 points, R1, R2. So how many forces do you ever calculate moment with? How many forces? Moments? 2. When A is the pivot, you've got tension and the 6G to calculate moments. So for the 6G, that's clockwise. Is it clockwise? Yes, clockwise. And T will be anti-clockwise. For 6G, that will be, should be straightforward because the moment should be 6G times the perpendicular distance, 2 meters. So take moments at A, the clockwise moments equals anti-clockwise moments. The clockwise moment is 6G times 2 meters. Okay, so that's clockwise moments. What about T then? Where is the perpendicular distance from the pivot A to T? So how can you draw a perpendicular line from A to T? That's always a bit tricky. So use a ruler to try to put everywhere. So try to put it. Yep, actually you can see that's a right angle. So that's your distance here. So that's your distance. That's your perpendicular distance. So that is the perpendicular distance. So how do you work it out? Well, that's a right angle. So the hypotenuse from A to C is 3 meters. The distance will be 3 sine 40. So the clockwise moments for T will be T times 3 sine 40. I'll draw the triangle out for you in case you need to see it. So A, and that's point C. Oops. Okay, that's point C. That's 3 meters. That's the distance we need. That's the right angle. That's a 40 degree. Okay, so using trigonometry, you can work out D equals 3 sine 40. So then we can work out T quite easily because 6G times 2. So T, if you rearrange the equation, it will be 6G times 2 divided by sine 40. So I'll put the whole thing in calculator, 6 times 9.8 times 2 divided by sine 40, close bracket, 182.9. So that'll be 183 Newton in 3SF. I'm going to store it in A. And just let me check my answer with myself, see if I've got it right. Not quite. What have I done wrong? 6G times 2 meters. 6G times 2 meters. 6G times 2 meters divided by 3 sine 40. Oh, I forgot the 3. Where's the 3 go? Sorry. Wondering. So 6G times 9.8 divided by 3 sine 40. My mistake. That would be 61 actually. So 60.98. So that would be 61 Newton 2SF. No, actually 3SF. Doesn't matter. So what I'm going to do is I'm going to store this in A. So I'm going to put this in A. So store it in A, 61 Newton. Next part. So let me have a read of question. I found tension ready, so that's done. Part B, find the magnitude and direction of the force exerted on the rod by the wall. So what force have we exerted onto the rod by the wall? So the forces exerted by the wall is a support other support forces R1 and R2. So they want you to find the magnitude of R1 and R2 and find the resulting force out of them. Anyway, so forces exerted on R1 and R2. So we essentially want to find R1 and R2. So we can sub into equation 1 and equation 2 subsequently to work out R1 and R2. So sub T equals 61 into equation 1. So equation 1 was R1 equals 58.8 minus T sine 40. So R1 equals 58.8 minus T sine 40. So 58.8 minus, I stored that 61 value into the calculator into A, so I'm going to press A sine 40. If you put in a calculator with me, you should get 19.6 Newton. I will suggest you to try to do it yourself as well. Try to put the value of T in the calculator and then try to put it in the calculator. You get 16.6 Newton for R1. And for R2 equals, so sub into 1 and 2, equation 2. So that's R2 equals T cos 40. So R2 equals T cos 40. So A cos 40, that's 46.7 Newton. Now that's not a full value, so I'm going to store it in B. Okay. To find the magnitude of R1 and R2, think about this. R1 is 19.6. R2 is 46.7. Now, if this is you, okay, in the corner, that particle is you. If you're being pulled upwards by 19.6 and pulled to the right by 46.7, in which way would you ultimately go? It'll be here, wouldn't it? That's the resulting force. So I can bring this, I can change this. If I move upwards arrow, if I move upwards arrow to the right side in here, that becomes a right angle triangle. So it'll become like this. So that will be our resulting force. But that will be our R1 and R2. Therefore, resultant force equal to square root of R1 squared plus R2 squared. So R1 is 19.6, so square root of 19.6 squared plus my B value squared, that will be 50.7 Newton 3SF. Now about direction, how to describe direction? To describe direction, you need the angle to help you. The angle will be here. So tan theta equals R1 over R2. So theta equals inverse tan of 19.6 over 46.7. When you calculate, we use the value B. So inverse tan of 19.6 over B value. Syntax error. Let's try again. 19.6 over B. Close a big bracket. That's 22.7 degrees. 22.7 degrees. So to describe direction, the angle is not enough. The direction, so direction is 22.7 degree. Now, the resultant force, the green resultant force is going upwards. That means going right and up. So that means it's away from the wall. Out means away from the wall. Up means above the horizontal. So that's the direction. 22.7 degree away from the wall and above the horizontal. Now that value 50.7 is quite important because that's how they calculate the bridge. So that not your hip as well. Well, I suppose the nature does it all. But this material in here, in this corner, in this pivot, this hinge, the material has to be strong enough to withstand all the angles when the bridge is drawn up. Let alone if there's a pigeon or there's a seagull sitting on there, that extra force on there, So that's why these are the engineering calculation. What material how much force does the material have to withstand when the bridge is being lifted up? So that's sort of a very simple way of calculating. What have we not included in here? Maybe air resistance, as I said, maybe a seagull sitting on there, maybe maybe when the material starts to deteriorate, does it add extra force? Does it take out extra force on a bridge, etc.? So you need to be calculating all that kind of calculations. That 50.7 essentially means the material must be able to withstand at least 50.7 degree when the bridge is drawn as lifted up to a certain angle in there. Okay, right. So that's the last bit. That's the hardest part about this chapter 7.4, the drawbridge scenario, and that's the end of the whole chapter 7 as well. You've learned, just a quick recap of what you've learned. The last page of notes. So particles versus bodies. So particle is what you've learned from chapter 7.1 to all the way apart from 7.4. What you do is you draw a force diagram, include force in X and Y direction only. If the force is not on the axis, so like this, no highlighter, crayon. So in an inclined plane, that's your axis. When the force 10 Newton is not on the axis, what do? Resolve it. By resolving, we mean we have to draw a right angle triangle like this, and that's your X, and that's your Y. Okay, resolve it, and then draw a force diagram to put in all the forces on there. Once you've done that, then you can use F equals ma in both X and Y direction. Usually on the Y direction, it'll be equilibrium, so you can let up equals down, but not for X. X will be F equals ma. Whichever side is the bigger force, let's say if the particle is sliding down, then you do downward force minus upward force. If the particle is being lifted up the slope, then you do upward force minus downward force. Then you obviously have to think about friction, pulley, tension, all that kind of stuff. Chapter 7.6, 7.3, from 7.3, 7.5, and 7.6. These are the key chapters for this part. And for the bodies, which is what we've went through chapter 7.4, you've got 3 scenarios. In these 3 scenarios, the difference is how we put in the forces, what direction and where are they placed. But they all have a common theme, which is the method. Step 1, you're going to resolve any forces that are not horizontal or vertical. For example, in this case, in the drawbridge we talk about the tension is not vertical or horizontal, it's diagonal. So we have to resolve T first. Once we solve t, they accept three equations. Up equals down, left equals right. And once you've done that, take moments at a point, we take moments at point A, and then clockwise moments equals anti-clockwise moments, and then the rest is just playing around those three equations. If you don't know what you're answering the question, just perform the steps. Chances are, if you do it correctly, you get a lot of marks anyway. All right, so that's the end of chapter 7. That's a big chapter.